Hello everybody. In this video, I am going to talk about the importance of requirement elicitation in ADAS feature development. I am sure everybody knows that in the V model, the top left step is requirement elicitation, which is an extremely defining step in ADAS feature development. We will further see elaborately the importance of the same step in this video. Now, why requirement elicitation is mission critical for ADAS? Understand this word carefully. Requirement elicitation is mission critical. It is not important or it is not prominent. It is critical. This word I am really emphasizing. Now, requirement elicitation is the single most leverageable step in ADAS feature development. All right. It translates into business user experience intent. What is the experience intent for ADAS features? Make driving safer and less stressful. Okay, so this intention is translated into precise, tangible, testable, and safe behaviors for systems that sense an open world, reason under uncertainty, and share control with human driver. In safety critical automotive development, which include standards like ASPICE, ISO 26262, ISO 21448, ISO 21434, which is the concerned standard for cybersecurity, weak or ambiguous requirements reliably cause late rework. Okay, so if your requirements are weak or ambiguous, they definitely cause delay, safety gaps, compliance failures, and costly homologation surprises. All right, strong elicitation prevents that. So taking care of this step in an immaculate, meticulous manner, it prevents costly surprises or delays. Now we will see below is an ADAS specific playbook that explains what to elicit, why it matters, and how to express it so engineering, safety, and validation can build and prove the feature. All right. So we will understand why this ADAS elicitation is very unique and important. Okay, I use the word hard in a very cautious manner because I personally believe that once you become an expert in ADAS, this becomes a routine step. But it no way undermines the importance. All right. The first important reason is human machine shared control. You must clearly define who does what, when automation versus driver, when the vehicle should be under automated condition, and when the driver can take over, and the exact handover rules. For example, what are the alerts, what are the timings, what are the fallbacks. And vague boundaries cause nuisance alerts or unsafe overtrust. Okay. Second is open world perception. Now, when it comes to open world perception, cameras, radars face weather, lighting occlusions, or they face the various types of weather anomalies, and requirements must quantify detection, false alarm targets, and operational design domain where they apply. Okay, so in the purview of the operational design domain, you must be very clear about where exactly they are applying. Next are the standards, which include the safety and SOTIF. It is not enough to avoid malfunctions, which come under the purview of ISO 26262, and which is the standard for functional safety. You must also handle safe performance of correct systems in unknown scenarios, which is governed by ISO 21448. That is the long tail. Now, when it comes to regulatory and ratings pressure, UNECE rules and consumer ratings encode scenarios and thresholds. If you don't elicit them upfront, you can pass lab tests but miss the star ratings. All right. So understand this very carefully. You don't elicit them upfront. If you don't elicit them upfront, you will pass the lab test and miss the star ratings. Now, these regulatory and ratings requirements are extremely important because unless you are approved by the or the OEM is approved by the regulatory bodies, you cannot sell the vehicle in the market in the first place. And even if you manage to sell, you will miss the star ratings, which are extremely important in the commercial perspective. Now, we are also going to see the cross-domain constraints: sensing, compute, thermal, power, cost packaging, and HMI must cohere. So there must be a proper coherence between all these various verticals. whether it is sensing or compute or thermal aspects or power aspects, cost, of course, cost because it's a business scenario, packaging, HMI must cohere. And good elicitation balances these early to avoid architecture churn. All right. So if you are very clear about elicitation at the beginning itself, this architectural gymnastics which may creep up at the later part of the development can be avoided upfront. Next is data-centric AI. Now, dataset scope, class taxonomies, and annotation policies or requirements. If they are implicit, ML performance plateaus in deployment. Okay, so machine learn performance may hit a plateau in deployment if the data-centric scope, data-centric policy requirements are not explicit, if they are implicit or if they are slightly vague, ambiguous. Now, when it comes to supplier ecosystem, sensors, ECU, maps, and middleware come from multiple vendors. So interface contracts and timing budgets must be explicit to avoid blame shifting late. So passing the buck or shifting the blame to some vendor at a later stage can be avoided if the supplier ecosystem requirements are also clearly elicited. Now, when it comes to OTA and cybersecurity, updatability, backward compatibility, diagnostics, logging, and threat mitigations must be designed in and not bolted on. All right. So all this, when it comes to OTA and cybersecurity, also all these mitigations, threat mitigations, okay, updatability, the backward compatibility, and diagnostics, all these things must be designed in. All right. And when it comes to the essential requirement set for ADAS features, you have to always think in layers. Every ADAS feature, for example, automatic emergency braking, lane keeping assist, adaptive cruise control, blind spot detection, traffic sign recognition, parking assist, needs requirement across these categories. First is user and operational design domain. What is the user intent? What is the user intent and value? Why exactly is that? What exact is that ADAS feature doing? Why exactly is that ADAS feature instilled in the vehicle? For example, automatic emergency braking, reduce rear-end collisions in urban driving. Now, when it comes to operation design domain, road types, speed range, traffic density, weather, lighting, map quality, lane marking, and regional differences. And also misuse and non-intended use. All right. When it comes to misuse and non-intended use, towing, roof boxes, camera covered, bumper damage must be taken into consideration. And next comes the functional behavior. Now, when it comes to functional behavior, the first is state machine, whether it is whether it is the state is off or standby or active or override or fault degraded. All these various states must be clearly outlined. Also, the triggers and inhibitions, what conditions arm, disarm, when, for example, minimum speed at which adaptive cruise control is triggered, hands-on detection, all these things must be clearly outlined. Next is behavior rules, longitudinal lateral response curves, jerk limits, gap policy, lane keeping authority limits, all these things must be clearly outlined and clearly noted. And next, when it comes to HMIs, alerts, tones, telltales, text, language, escalation ladder, driver takeover requests, the various types of chimes, all these things are a part of the HMI. Now, when it comes to perception performance, you should be aware of the class of the vehicle, whether this particular vehicle is able to perceive a vehicle, whether it's a truck or a motorcycle or a bicycle or a pedestrian or an animal or a lane line or a road edges, whether it is just a traffic cone or a barrier. All these things must perception of all these things must be clearly noted. And KPI is nothing but a metric. And for developing the feature, probability of detection, false alarm rate, position velocity error, time to alert, confusion metrics for key confusers, example, plastic bag versus pedestrian, minimum detectable size, occlusion tolerance. These are the various metrics that must be clearly considered and outlined. Next is latency budget. Now, when it comes to latency budget, what is the uh, time lag between a camera exposure and actual uh, actuation deadline? How rapidly is actuation or actuator taking the necessary action the moment the sensor is exposed? All right. Now coming to the planning and control, stability and comfort. Okay. First you plan the stability and comfort. What is the maximum acceleration and deceleration? What magnitude of jerk? What is the lateral acceleration? What is the swarm behavior in dense traffic? And also fallbacks and degradations. What happens on sensor failure, bad weather, low confidence, when it is a low confidence, it reduces the authority, it increases the gap. You should alert the driver or disable the future. All right. Now, when it comes to safety and SOTIF, you have to take into consideration hazard analysis and risk assessment, from which safety goals are derived and from which ASIL, automotive safety integrated levels, are derived. And this ASIL level clearly explains the hazards, the controllability, the exposure, the severity, safety mechanisms, diagnostics, safe states. And when it comes to SOTIF strategy, scenario discovery, unknown safe mitigation, driver over trust, countermeasures. All right. So these strategies also should be clearly identified during the requirement elicitation. Now, when it comes to cybersecurity and privacy, which is governed by ISO 21434, okay, I'll just write it down. ISO 21434. Now, this is the standard which is governing the cybersecurity and privacy. So the TARA outcome must be clearly analyzed. Data governance like logging scope, retention, pill handling, principal handling on a device and backend analytics. Okay, and also these requirements must be verifiable and validatable. Okay, so when it comes to verification, whether it is a normal verification or an edge verification or misuse cases with the parameter ranges, covering coverage matrix like ODD coverage, when either the whole ODD is tested, scenario combinatorics, data coverage, requirements to test traceability, and benchmarks and rating, which regulatory NCAP protocols applied and what pass means. Okay, so this clear outlining, clear knowledge or clear notes about verification and validation must be outlined. Next comes the architecture interfaces. So when it comes to sensor contracts, field of view, range, refresh rate, accuracy, self calibration, heater washer controls. Okay, I'm sure everybody knows that there are some modern state of art vehicles in which the sensor is cleaned by itself. Okay, so under in that scenario, sensor contract has to be clearly, you should be very clear about the sensor contract. And when it comes to compute and comms, CPU, GPU, NPU budgets, memory, network bandwidth, determination constraints. So you must be very clear about which protocol, whether it's a CAN protocol or a flexible protocol or Ethernet protocol, is going to be used from sensor to the ECU, or what is the protocol which is being used during the diagnostics. All these things must be very clearly articulated. Now, when it comes to interfaces, signal names, units, rates, timing guarantees, and error semantics. Okay. Now, coming to the production, service, and cost. All right. So all this design is fair enough, is good, but the most important thing is it must be productionable and it must be manufacturable. So manufacturing tolerances and calibration, end of the line checks, field service procedures, bill of material, thermal power envelopes, and trade-offs must be clearly outlined. Okay, all these things must be clearly outlined. All right. The whole purpose of this exercise is to turn vague intentions into testable requirements. All the ambiguous intentions or ambiguous requirements must be articulated into testable, tangible requirements. Okay, let's see this with a worked example. For example, automatic emergency braking, and some people call autonomous emergency braking also. Now, system, what is the vague requirement? What is the basic necessity of automatic emergency braking? System should avoid pedestrian collisions in city driving. Okay, now after what are the various elicited, quantified, and tangible outcomes? When it comes to operation design domain, first is in urban paved road at a velocity of range 10 to 60 km per hour, daylight and night time with street lighting greater than 2 lux. Okay, again, this is important. Street lighting greater than 2 lux, whether it is a dry road or a wet road, no heavy fog and snow, especially in a country like India, you can safely assume that there is no heavy fog and snow, and front camera plus front radar operational. When front camera and front radar operational, this must be satisfied. This must be able to function. That is the ODD. Now, when it comes to detection metric or detection KPI for adult pedestrians crossing laterally at 5 to 8 kilometer per hour. So it is, you estimate usually pedestrians, adult pedestrians when they are crossing the road, they are crossing at the velocity of 5 to 8 kilometer per hour, and PD greater than or equal to 95% at FAR less than 1 per hour, frequency less than 1 per hour, and range is distance is greater than 40 meters, and lateral position RMSE is less than or equal to 0.25 meter, and RMSE is less than or equal to 0.5 meter per second. Now, when it comes to timing collision estimation latency may be less than or equal to 60 milliseconds, 95th percentile. So on the average, estimation latency is 60 milliseconds, and decision to brake delay is 80 milliseconds. Now, coming to the behavior, if time to collision is less than 1.6 seconds and driver does not apply greater than 0.3 G within 400 milliseconds of the warning, system applies autonomous brake up to 0.6 G and jerk limited to 12 meter per second cube. Okay, so this is how the system should behave. And when it comes to human machine interface, single chime plus HUD icon at human user display icon at TTC 2.0 seconds. Now continuous tone plus red cluster at TTC is equal to 1.6 seconds with brake preparation. All right, so this continuous tone and red display should happen if time to collision is 1.6 seconds with brake preparation, and driver steering override is greater than 2 Newton per meter cancels the autonomous brake. If the driver is alert and if a driver presses gives greater than 2 Newton meter, it cancels the autonomous brake. Now, when it comes to degradation, if camera confidence less than 0.4 due to glare or radar misalignment fault, AEB dearms and informs driver. AEB limited logs GTC XYZ. So, if at all this any degradation happens, if any fault happens, any degradation of the sensor happens, then a DTC immediately is logged, or a freeze frame is immediately logged, which can be XYZ. Now, DTC nomenclature is beyond the scope of this particular video. Just understand that a DTC will be logged. Now, when it comes to validation acceptance, pause 4850 runs across the scenario matrix. All right, so in the simulation across the 48 to 50 runs, whether with the adult or child dummy sizes, different clothing colors, occlusion percentages, approaches angle, lighting bins, and you have to meet the NCAP protocol of X targets for pedestrian AAV. Out of the 48 to 50, this must work effectively for X targets as per the NCAP protocol. The level of precision turns an idea into design inputs, test cases, and safety case evidence. Okay, so hope all of you are getting a clear-cut idea about the importance of this requirement elicitation and what are the various steps that are involved in the requirement elicitation. Now, to proceed further, scenario catalog and coverage, your validation backbone. Now, during elicitation, build a scenario library tied to each requirement. Whether it is a nominal scenario or a edge scenario or a misuse abuse scenario. Okay, when it's a nominal scenario, you assume a straight crossing pedestrian and a clear day. And when it comes to edge, partial occlusion by parked van, low contrast clothing at dusk, heavy backlight, wet road reflections. And when it comes to misuse, sensor blocked by sticker after market bull bar and camera tilted after windshield replacement. Okay, so these are all the how to say eccentric scenarios a requirement elicitation engineer must be able to predict. Now for each scenario, capture parameters like speeds, distances, illumination, occlusion, road friction. Okay, these are all the parameters that must be captured, and also expected behavior, KPIs, and pass fail thresholds. This directly feeds the simulation, proving ground runs and on-road testing. Provides objective evidence for safety and rating. Timing budgets and interface contacts. Okay, now understand this timing budget and also interface contracts. Now elicitation must close the loop on timing and interfaces. So there must absolutely be no ambiguity about what are the various timing budgets and what are the various interfaces. For example, end-to-end latency budget is it should be less than 150 milliseconds for automatic emergency braking from photon into brake pressure rise. Okay, from the moment data is captured to brake pressure is applied, it should not exceed 150 milliseconds. All right, now when it comes to per block allocations, ISP 250 20 milliseconds, perception 50 milliseconds, fusion 15 milliseconds, planning 10 milliseconds, actuation 40 milliseconds, and margin 15 milliseconds. So this many activities must happen within this 150 milliseconds. Now, when it comes to interface specifications with units and rates, lane curvature, 50 head time stamped and max jitter is 5 milliseconds. So ambiguity here is the leading cause of works on my ECU and integration failures. All right. So all these time budgets must be as clear and there must be utmost clarity and accuracy in these time budgets. And this sentence is important. Ambiguity in these timing budgets can lead to integration failures. Is it clear? Now, when it comes to elicitation techniques, now this is all the importance of elicitation. Now, we are going to talk about the various types of elicitation techniques that work well in ADAS. Now, in ADAS, first elicitation technique is stakeholder workshop, product, safety, legal, HMI, validation, quality, field service, suppliers. All these various stakeholders' opinions or point of views must be taken into consideration before you finalize the safety stakeholder requirements. When it comes to legal requirements, experts of HARA and SOTIF, they must be put in a place, and their opinions also must be clearly considered because they form the building blocks of the requirements. Now, when it comes to data-driven discovery, mine fleet telematics, public data sets, and quantify real ODD distributions. All right, next is misuse and red teaming. Systematically invent problematic cases, include environmental and human factors. So a elicitation engineer must be able to imagine a misuse scenario. Okay, even that falls under the purview of a elicitation engineer. Now coming to the prototyping and wizard of Oz rights, observe driver's reaction to alerts, intervention before locking HMI. Now coming to the competitive benchmarking, map target ratings, regulatory protocols to concrete requirements. Also Gemba with service teams. Gemba is nothing but workplace. So elicit in the workplace, requirements like calibration, alignment, and post-repair procedures is extremely important, especially for sensor alignment and calibration. This step is of utmost importance. Now, when it comes to common failure modes, what are the common failure modes and how elicitation avoids them? How does elicitation engineer ensure that common failure modes are avoided? First is he must avoid the ambiguous terms like bad weather and reliable detection. Okay, He must always replace these ambiguous terms with a tangible, replace with measurable bins and thresholds. A tangible mathematical threshold must be clearly described or noted. Hidden ODD assumptions. Write a explicit ODD and default behavior when outside it. All right, ODD must be explicitly written in as elaborate possible as possible. All right, next is ignoring degraded modes and define censor out low confidence behaviors upfront. Fourth is over promising versus compute thermal. Now co-design requirements with hardware and packaging teams. All right, now when it comes to no traceability, every requirement links to test, hazard safety goal and an interface. So lack of traceability is a common failure mode, and that must be avoided by ensuring that every requirement is testable, or it is a safety goal that must be, or a safety goal or interface. It must be traceable to one of these. Also, there should not be any data gaps. Specific dataset composition, class definitions, annotation quality requirements. All right, and when it comes to supplier misalignment, freeze interface contracts, add acceptance test to contract. In the contract, what are all the approval tests, what are all the acceptance tests? They must be clearly given to the supplier. There must not be any kind of any even minuscule ambiguity when it comes to supplier product approval. So at the end of elicitation, what are all the deliveries you are left with? First is you are left with a feature vision and a ODD document. Next is system software requirement specification. All right, understand this carefully. System software requirement specification. Next is state machines and HMI behavior specifications. I hope everybody understand what the state machine is. State machine is nothing but the ambient state, the environmental state in which the machine is working. Whether it is a snow, fog, rain, or muddy condition, that is called state machine. Now again, you must have a perception KPI and latency budget. Also, safety case inputs, HARA safety goals, ASILs, safety mechanisms, and SOTIF augmentation plan and unknown unsafe mitigation list. Now, cyber security, TARA summary and controls, scenario catalog and coverage targets, interface control documents, acronymed as ICDs, validation strategy and pass criteria mapped to requirements. And also traceability matrix. The traceability matrix, there are a lot of tools like Polarian, Doors, especially this Polarian is becoming very popular in tier 1 and OEMs as a part of the requirement software. Okay, of course Doors is also equally popular, but nowadays this Polarian is making more and more advent into the market. Now let me briefly touch upon a lightweight requirement template you can reuse. For example, automatic emergency braking feature. Title product, it is pedestrian detection probability in urban daylight. So this is the state machine, or the this is the state in which this is supposed to work properly. All right, first you define the context ODD. Urban paved roads, you are driving at 10 to 60 km/h, daylight is greater than 2 lux, or drive at condition, front camera and radar are healthy. And when it comes to requirement, the system shall detect adult pedestrians crossing at 5 to 8 km/h within 40 meter ahead, and with PD pedestrian detection greater than 95% and at frequency actuation rate less than 1 per hour. And also the verification, like simulation in 1000 cases, proving ground 20 runs, on road, NCAP protocol alignment. These are all the various types of verification. Also, you should take care of the dependencies like sensor field of view, ISP latency, perception cycle time. These are all clearly mentioned here. And also the safety link, the ICT signals, the degraded behavior. If confidence is less than 0.4, if at all the sensor confidence is degrading, what should be the backup step? All right. For example, in this case, the driver must be immediately alerted that your AEB feature has degraded, and you must be as alert as possible. It is like indirectly telling the driver, don't rely on AEB anymore. That is the clear-cut message given by this feature. Okay, so A quick starter checklist. Let's touch upon the quick starter checklist. If at all anybody is new to the elicitation, this is a checklist that they must have. ODD is fully defined, functional state with triggers, inhibitions, and overrides, perception KPIs, latency budgets, class taxonomy, annotation policy. And when it comes to HMI alerts with thresholds and timings, user experience validated with users, safety goals and SOTIF scenarios, degraded limp modes, diagnostics, diagnostic trouble codes, service procedures, cyber security controls, logging in, privacy requirements, and scenario catalog with coverage targets and acceptance criteria. So interface contracts, signals, units, rates, timing, error, semantics. And last but not the least, the traceability is clearly established in the ALM tool. ALM tool is nothing but whether it is a Polarian or DOORS, which I touched upon in the previous slide. Okay, so hope I gave an extensive overview about the importance of or the prominence of requirement elicitation in development of any ADAS feature along with an example. Okay, hope everybody definitely gets educated with the help of this video. Thank you so much.